Hi, this is Bill Foote, along with the team, uh, to have a discussion about the waiting time model. And we are in week 5 of spreadsheet decision modeling. And what you see on the screen right now is the beginnings of this fascinating model for the eatery. It's actually based upon some operation models uh, that have been used pretty successfully, but it's a very, very basic kind of model that we can use to relate, in this case, the amount of time for waiting. But you can imagine lots of other situations with this. With that, I just want to open the floor. I do know there are some questions, and Charlie, perhaps you can lead the congregation in prayer here.
So just going through the simulation and trying to understand the computation using the index match function, number one, and how I understand the eatery ID numbers, the morning and afternoon shift, but just again, I know we've done some index match in the past, but just another refresher on that would be helpful.
Sure. And just to give a little bit of background, we are starting with some assumptions. They're over here on the left, where we have the mean AM number of minutes in a waiting line. That's at 3.5 minutes, and the mean B is how many minutes more or less than the average morning do we have in the afternoon. So this is really PM. To notice that, and AM, and notice every time you do something, it shifts. The purpose of this model, and they also have standard deviations. They can 3.5 can vary up and down. The -1 can vary up and down by some amount, and that will be guided by the standard deviations. But the innovation of this model was to put in something that related morning and afternoon. There might be a production process behind this, for example, that relates morning and afternoon, or one phase in another in a value chain, a supply chain, for example. That is the idea behind it. And in this case, they're negatively related. We also have sigma and numbers of visits and numbers of eateries, and we have a couple of other parameters to consider here. There are 20 eateries in this particular model, 20 different. I can remember using a model similar to this at New Process Gear, which was a joint venture between Chrysler, GM, and Toyota, where they were making transmissions. And they had, I don't know, 38 different stations. And we use exactly a model like this. It's the eatery ID is independent stations and so on. In that model, we actually correlated the stations, in this case, the eateries as well. So there's all sorts of ways to manage this, and we'll get to the index match. This one is using the Cholesky transform discussed in the text to relate random variables x1 and x2 for these are correlated just to keep generating that. The eatery parameters, notice the mid here. Here's one right, almost not in the middle. Is it one in the middle? Here's one in the middle. It can be as high as 4 and as low. Here's the middle again. Got a small one here. Yeah, 1.79. And that is correlated with in this case, the deduction from the average in the morning for the afternoon. And those are correlated, and you can see they're around 1 pretty much. You get some smaller ones as well, like this minus 0.81 and 0.71 on the top. Okay, these are all correlated. Now, the idea of the model is to use these parameters for each and every eatery in a further simulation. So we're doing a simulation on a simulation just to make things more confusing. Oh, and it's also interesting just to, look at the correlation between A and B parameters. So what does the model look like? The way I write these models is here's the mean waiting time, and it can be it has one of two states, AM and PM. Okay, so if it's just AM, you get A. If it's AM and PM, if it's PM rather, you get A minus B times 1. It's that 1. So this is A minus B times 0. So all this is basically a model that says the mean can take on one of two values, A minus B, or just A. That's all. It's that simple kind of a model. It's actually like a classification model that is used in machine learning. Okay, very, very, very simple model. But it is relating a state. Is it on or is it off? That's the idea of the 1 and the 0. If we get to the second simulation, which gets right to Charlie's question. See if I can bring this up without impaling ourselves here. Okay, let's try this again. There we go. And accessibility, how did that come up? Fascinating. Okay, this is where the index matches occur. Now this first one, F3, is basically calculating the mu again. And the first index match is to look at a variable, is to index a eatery. Now, what's a eatery? Back here. These are the random. Do this. You can see that it appears up here as a eatery. These are the random values of the A parameter that we're simulating. And they're correlated with the B parameter. Okay, so that's the B eatery. So we're indexing that. We're looking through here and we're trying to find the eatery. So we're just trying to pick the right one, basically. And that's what the index is trying to do. So it's by eatery, which will index by I, plus, and then the second index B eatery matching D3. What is D3? It's the eatery ID. It's just the eatery ID. So if it's eatery 5, we're looking for A in this list over here, looking for A. Okay, we're looking for this number. Okay, we're going to be looking for that number. We will put it here. Okay, and then we will add B for eatery 5. Simply times 1. Times E3. times E3. Now, E3 is this thing called A. And A can take on a value of 1 or 0. And thus we have a simulation of not only A and B instances, which are correlated with one another, but we have a simulation of how often somebody arrives. So they arrive, yes, they arrive, no. Okay. And that arrival rate, if we look at it, is done very, very simply with this rand. If the random number, and rand is just a number between 0 and 1, if it's, unless it looks like a probability, huh? You agree with that, Charlie? That that's what it is. If the random number is 0.3, the question is it greater than PAM? Well, what's PAM? Oh, 0.5, happens to be 0.5 in this model, which means there's a 50-50 chance of it being somebody arriving in the morning. Okay, that's, that's the kind of idea. If it's greater than that, if it's greater than 50, then assign a 0. A 0 means AM only. If it's less than 50%, assign a 1. So here we have morning, afternoon, 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 morning, afternoon, 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 and so on. Morning, afternoon, 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 and so on down the way. So this is like an acceptance rate. And I only mention that because of Stan Ulam, who had surgery, and he was on the Monte Carlo project, and he created the Monte Carlo project, which helped build hydrogen bombs, but we won't go into that. During World War II, that was Monte Carlo was the code name for the project. The thing to remember here is you have an acceptance rate, and the acceptance is around, is this random number greater than the acceptable rate? That's all. We could have changed this to 0.6. We could have put it to 0.4. That's another day. All right. So just knowing what's in this formula first is where we're at. So the first index locates the A, index match. The second one locates the B. Okay, and the formula then takes the A plus the B times a zero-one distribution of an arrival. Does the arrival actually occur? So let's look into the anatomy of index A eatery, match D3 eatery ID, and 0. 0 means an exact match, by the way. So all we're doing here, so let me write this in here, equals index. Now, what are we indexing? That's the first thing I ask. We're indexing, this is the result we want. We're indexing these. Okay, so that's A eatery. Okay, fine. Okay, go back here. So we're indexing A underscore eatery. Notice we had already made it a, and I do this like religiously. I don't, I literally put everything into a data dictionary, and the way you do that in Excel is you make everything a named range as much as possible. I know it can get confusing. You can print out the named ranges, by the way. That is a way that there is a way to do that. Maybe we'll show that later. So in this, find which one of these do we want? We want the one whose row is this. Match that eatery, for example. I'm just doing an example here. Match that eatery. And where do we look for that? Well, that's in over here again, eatery ID. Okay, match it in here. So it'll be in here. It'll be 5, which is easy. You could have just put a 5 in there. That's fine. But match it in here. We know that's the row. Okay. So find the row number, which is eatery ID. Make it an exact match. And it should be 4.2248. Okay, is it? Yep, here it is. It is. Okay, so we got that part. We got the intercept. Okay, now let's work on the slope. That's equals index. Is this helping at all?
Yes, sorry, I was muted there, but
No,
yeah.
that, all right. Mute yourself. Yeah, yeah. Index match. I use it. I don't actually have to use it very much. I don't have to do the match here at all because eateries are already the row numbers. Okay, I get that. I understand that, everybody, the universe. But I do it because it literally documents what the calculation is, what the data query is. So look in this case, B eatery. I'm also looking for, I think row 5 here, eatery number 5. And again, I could have, instead of the match, I could have just put the row in, it would still have worked, but it won't be documented. And look at that in eatery ID. This is called not hard coding it, okay? That's the idea. 0. Okay, so notice we have a situation. Well, it changed every time you play with this, it changes. Okay, that's important to realize. Random numbers. It forces the mind of the modeler to abstract from even the abstraction called the model here, because the random numbers change. Okay, I'm not going to apologize for that, but that is what is happening. So now I have A, now I have B. Now the interesting thing is what does the arrival itself, the big A, the big A here. And I said that was an if statement. If brand, well, first of all, just look at what brand does. Just equals. Okay, it gives you a number between 0 and 1. That's all rand does. So okay, now let's memorialize that into a formula. If rand, okay, put a space in there for my old eyes. No, come on. Yes, I know it's not going to work. No kidding. There we go. If that number is greater than PAM, see where that was. Remember that was set at 0.5. It's a 50-50 chance. Okay. Then make it, if it's greater than that, make it, in other words, if it turns out to be 0.7, for example, the random number is just, ice in a little jar that you and throw against the wall. Okay, it's all that is. A sign is 0. Otherwise, say it's that. and get that. Okay, if it's greater than that, it is AM. Otherwise, make it a 1 so that it becomes PM. Okay, in this case, it's that. So we just compile the formulas. This number plus this number times the event of arrival itself. Oh, that time it was 0. So you see, when it's 0, it's just AM. Let's see if we can do this again. Okay, it's still AM. Notice you still get the correlated A and B parameters. There we go. And you see the deduction. 4 minus 1 gives us 3 in that particular case. So we had 3 instances, only had one of these. Okay, does that help at all? Or are we clear as mud still?
No, that
Okay, so that's mu. So that's what we're simulating here. And we haven't even got into the delicacies of Cholesky and all of that. I've been teaching, and I teach this at the undergraduate level. They're like confused. Why do we want to do that? Well, that's actually a really good question. Why would you want to do that? So math for me is just advanced logic. That's all it is. I'm not a mathematician. I'm not a logician. I'm a human being that needs to systematically look at stuff, whatever this stuff is. And the math helps me to do that. Math, for example, the way I do statistics, I don't do it the normal statistics way. As you can see already, I'm not bent that way. I'm bent in a very different way. I was raised in a tradition more philosophical, I guess, and case by case. I'm not an anthropologist, but everybody tells me I act like an anthropologist, not like an economist. And I go like, whatever strings your fiddle, we used to say.
I like the analogies that you gave with the, it just shows the progression when you talked about going for a shot. So it's not only going for the shot, but it's having the supplies and it's having the space and having the people on hand and having the staff and the security. And so it's a progression and a logic of, okay, if this is the parameters, then this is what we need to make it efficient or successful.
Yeah. Thanks for that. I mean, it's just, somebody was asking me, where did you learn management at all? And I'm just going to show where I learned management, and everybody's going to go like, are you kidding me? Okay, here it is. You see that? Now you see that cheery faced young white boy there. It's like, yeah. I mean that was kind of how we grew up, I guess. But I love the background. I just love the kind of backgrounds. Handbook for patrol leaders, unbelievable. And you start looking through this, it actually teaches you how to budget. I mean, and put the schedule together. These things sound familiar? And it says, and there's a psychology component, a big one, 2 of them. It literally looks at the psychology of, there's 5 types of boys in every patrol. And there are, in all of my teams, there are these same 5 types of, there's the bully, there's the one that's withdrawn, and there's a bunch of kinds of, and what they describe is, how do each one of these people help one another? Oh, I mean, that sounds like pretty good humanistic stuff. It was written by William Hillcourt, and I think the first edition of this is 19 This is a 1963 printing. I got it hot off the press, apparently. I think this is 1940. Incredible. And I'm going, you know, and it shows you how to make charts and tables and how to put together an agenda for a meeting and all of that kind of stuff. And when you start looking at models like this, it's exactly how you pulled it apart. You know, we're doing this. The purpose of this is not to, you know, be masochistic and use weird math or anything like that, but it's for a resource allocation problem. So thank you for that. That was, I just had to bring Francesca. I'm sorry if you saw that. I just had to bring in the
No worries.
Control Leader Handbook, and the guy sitting behind me over here. That's Dante. That's one of my other sources of when I get stuck. So Dante always has something good to say. I think that's his death mask. Oh God, I inherited that. Well, it's not mine. It's my son's. That's from his grandma. Let me get back to business here. These interludes. So okay, so now we have these parameters, and we have a simulation over here. Let's just go through this. So I have something called a key here. I don't think I actually use the key anywhere, do I? I might be using the key somewhere. Let me see where. Oh yes, I think I know where it comes up. So we have different runs. I'm only doing 2,000 runs. My usual number is 10,000 runs. Why? I just like to do it a lot. All right. And it's Mike Schrage and George Gilder. Waste transistors, and if you have a lot of transistors, waste simulations. I don't mean waste in the sense. It means use them. Use them. You know, until you actually have to show up and make the decision. We have 20 eateries. So this is set up this way. And then another 20. I didn't put code in for this. There's a way to do this, every 20 times. And guess what? It uses index and match, but we won't go into that. And so you just keep doing this, and that's why it's 2,000. Look at that. Why is that? Oh, that's interesting. Ah, very good. Okay, so we have that. I was just looking at the way this worked out. It almost looks like a date. Interesting. Sorry about that. So we have the run, we have the eateries. So we're doing 20 eateries at a time, 100, 20 eateries at a time, 100 times, right? Is that correct? That's 2,000?
2,000, yes.
So if you think about it, you're only running 100 simulations for each and every eatery. That's it. Only 100 simulations. That's why I probably would have done this instead of 100. I would do it times 1,000 simulations for each. And then I think you get 20,000, right? You get the idea of how many times we're doing an actual simulation. The way I also think about it is, yeah, you just did 2,000 and go, not quite. You go, that's not, the common denominator is eatery ID. That's the common denominator. There's 20, 20, 20, 20. So at the common denominator, eatery number one is only 100. So this is just a simulation of 100 across 20 eateries. And that's another aspect of this to think about from a modeling point of view. All right, what's this one? Sigma weight times norm inverse V ramp. What the heck is that? F3. What is F3? Oh, it's the mu plus something there. Huh. Let's look at that. Okay. That's the next thing that we do have to understand is F4. In the end, We want to know the minutes being that we're waiting. Okay, so the wait, I mean, you could say it's this, that randomly changes all the time, but we're adding what we used to call mu is the systematic component. And there's added to this systematic component, the actual model looks like this. Mu is normally distributed with a mean equal to A plus B I. That's the mean. I'm sorry. I'm sorry. W. The wait time itself is distributed with a mean, which is composed of the A and the B and a randomly occurring arrival event itself, where A and B are also correlated with one another. It's a pretty sophisticated model. Even though it's just a few parameters, a lot of interesting sprockets and slide bars and other things, and as we crank it, okay, comma. Now the rest of it is there's a sigma, because it's normal distribution, the sigma of the wait time. So somehow, if we know mu, we know sigma. Each and every one of these, we do know mu, like this one, 2.99973, right? We have to take mu. So, I mean, actually, how do we get this? Take mu, one of these mu's, add to it sigma is a scaling factor. That's all it is. But it scales something. So that's the scaling factor. What it scales is the number of standard deviations. That's what it's scaling. And we're also going to randomize that. This is indeed the complete model. Okay. Does that make sense? A little bit make sense? I mean, this is the unsystematic component. If I was epistemologically minded in this generalized empirical method that I use every day, I call this a statistical residue. Due to the fact that I just don't know everything there is to know about a particular anything, okay? Everything I do is I'm making a model of that which I observe outside of myself. Okay, I try to bring that in to myself and figure it out, but there's always something that I don't quite get, right? That's called the statistical residue. You're never going to be able to figure out every single customer's behavior, and you will be surprised. That's the statistical residue. The mu part is, well, we're far less surprised there, and that's why we're simulating that. And then we're also simulating the surprise itself. Surprise. Okay, there's a surprise. But another way of looking at this, you may know this from basic stats, subtract mu from both sides. Divide both sides by sigma. Anything divided by itself, of course, is equal to 1, and 1 times anything is itself. Beautiful. That's the z-score. The z-score always has, and this is again from basic stats, always has a mean of 0 and a standard deviation of 1. It's like written in stone. You can't change it. It's mathematics. It's logic. You can't try to change it, but I think the universe would be a little bit different. The red shift would be a blue shift. The Big Bang would be a little whimper. Okay, something like that. So here's our real model with a parameterization of surprise. How much surprise? So we're like doing everything here. We're saying, where do things tend and how do they deviate? And how much deviation is the Z? It actually tells you if things deviate on average sigma W, Z tells you how high are you going to have to jump? How low are you going to have to go? Okay, above and below the bar. The bar is the mu. Okay. So that's the rest of the story. So we have mu. And now we have to add sigmas times the Z. Okay. You have to add sigma times the Z to that to get a waiting number of minutes. The average waiting time is the average number of minutes. So up here I have sigma Z times norm inverse of a random number. That's a little bit different than the distribution. So let's just do this down here. Let me just do Z first. So if random number, if it's below 0.5, Z will be minus half a standard deviation below the mean. That's the idea. Z is telling you how many standard deviations above and below the mean. This time it's below the mean because it's minus. If the random number is a little different. One standard deviation, 1.03, one standard deviations above the mean. Okay, so this gets randomized. We scale it again, multiplied by, and this is called, definitely it's called the residual. So we take this times, now there's a parameter that we specified back here called sigma weight, 0.5, half a minute. That's the amount of spread, the amount of average surprise. Okay. And we have this sigma weight. That's the average surprise. So the amount of waiting time will be equal to mu plus the residual. So it's a little bit above, a little bit below. This time it's below. The surprise is below. And this kind of helps us fine tune it. Okay. So that's the rest of that story.
I thought your the other illustration was very helpful. The bell curve for the morning, and then the afternoon was a little steeper. And then when you combine them, you see you see them together. I thought that, I guess I'm more visual in that sense. It comes together when I listen to your explanation here, but then see the visual aspect as well. Yeah.
So it's this one. There's the average.
Right.
And then we splice it together with
PM.
another average,
Mhm.
which actually kind of goes like this. Okay, so those two produce a new one when you convolve them together, one with the other, one with the other, one with the other, and so on. And you get a new one that looks maybe like that, or maybe a little bit more like that. There we go. Okay, so that is true. So that's a distribution of mu. And then we add on top of that, okay, this. And this is the Z stuff, right? It would look like, all right, it's the random number is actually uniformly distributed. That does something to this.
Right.
And finally, it probably gets around like that, right? But whatever it comes to, all right, whatever it convolves to, exactly. That's great. That's Charlie. That's right. The visual is always better. I'm actually a visual artist on the side, or actually, I do this on the side, and that's really what I like doing. And I'll show you pictures sometime. But my Instagram handle for all of you out there is this. You can see the kind of stuff I like doing. Painting and drawing, and it's figures and landscapes and seascapes. So all that kind of stuff. I'd rather be visual too. Oh, well, that was fun. Okay, I hope that was helpful. A little bit helpful anyway.
Yes, very helpful. Thank you.
Okay. And then the last part of this is, well, how do you visualize it? And this visualization starts with putting together a grid that we're going to use to visualize something. In this case, the weight. And I'm using a technique called indirect. The indirect of a value in a cell. If the value in the cell is weight, and weight is a named range, indirect will point anything you operate on it, like a min, a max, anything, to that range. That's really cool. I think that's very cool that we can do that. It allows me to actually build applications for clients in a very clever way. But here's the standard thing over here in EDA, which stands for John Tukey's exploratory data analysis. We have min, we have a 25, 50, and 75 percentile. Those are cumulative. And we have the values of weight that we simulated. And this is across all eateries, AM and PM. Okay, this is a gross depiction of everything. Here's the max. The IQR is the difference between 75 and 25. We have the average waiting time, which is that overall, and the sigma of waiting time overall over all the iterators. Remember all the correlations, all of that's into this. Remarkable. So if you have a AM/PM staff, you're going to have to use enough resources for an average service of 3.49 minutes, plus or minus that. Okay, and mean absolute deviation is just a little bit more robust way of looking at a sigma. And skewness, very little, kind of kurtotic, kind of thick-tailed. You're going to have some surprises. You're going to have some surprises. That's what that means. We'll go into that another time, perhaps. Kurtosis is also how volatile is your volatility? How volatile are your surprises? How volatile? In this case, it's actually not very volatile. See what else we have over here. So we use the grid to create a, now you could, there's a function in analysis tool pack called histogram. And if you configure it properly, you can get all of this. I prefer to do this because it's understanding what goes into a histogram. That's why. It's more pedagogical than anything else. So I make a 21-point grid. Each interval has a beginning and an end, and they're non-overlapping. So the beginning goes to the end. So we're looking for the number of things in weight, just the number of weights in between this beginning, but not including the end, up to but not including the beginning, but up to and not including the end, except for the last one. So we don't get in trouble with the accountants who wants to make sure that you're counting everything, not over, not under, no over and shorts jar, which is what we used to have in the bank branches, but right on, okay? And you can see that this will give us, we add up all of these counts, which are called frequencies. And the bottom, it should say 2000, yep, 2000. Relative frequency is just frequency divided by 2000. And that is now a true probability plausibility index. What is the most likely wait time? And we use mid for that, mid of each of the intervals to get the most likely. I think it's right here. 1070, yeah, most likely wait time is 3.44. Kind of close to the one down here. Kind of close to this. This is a symmetric distribution because the median and the arithmetic mean are equal. Okay, converging. Very, very probably is normal. Normal distribution. We're using normal distribution in a lot of stuff here. We could use a Poisson distribution for the wait times. We could do all sorts of things. We're not. Okay, there we go. Yeah, it looks like that. And the cumulative is taking, that's the first one. The cumulative takes the previous and adds the increment. Relative frequencies are increments. You're actually computing in calculus an integral. The area under the blue curve on the right is this curve right here, also called the ogive for all of you woodworkers. Take a cross section of a piece of molding and you got an ogive, usually, the S curve. You also use this for technology diffusion, where we start low, go up, we get to an inflection point, which is right here, by the way, where these things begin to turn as well, exactly the same spot, and then decreasing returns. Better start building that new technology, right? Okay. Increasing returns at the inflection point. So there's a lot of work that goes on in startups on figuring out where the heck this thing is. And this is a way, again, of systematically thinking about that. Okay, so we found a lot of stuff into these. Over here, you can also build a pure PM simulation and a pure AM simulation, should you want to do such a thing. Okay. How did I do that? Oh, no, don't worry about that. These are all ones, right? That's PM. And the AM are all zeros.
Yeah.
So you could use these simulations too, just to get at morning versus afternoon, just by setting A to 0 or A to 1. That's if it wasn't for the fact that we have a PM shift, the wait time would be, okay, the 4 of every lawyer I have ever had to use in contract negotiations. But for this, all the little carve outs in the contracts. Okay, so I think that's what it's all about. I think we answered the question, right?
We did.
Yeah, okay. One last thing. This is what I teach the undergraduates all the time, and we'll have it located here. We posed the question. We have resource issues. What's the average wait time, are we ever surprised, pose. We formed a bunch of hypotheses. Those were the A and B parameters and their correlation. We built a sampling. This is called a generative model. And I have forced people that have worked for me for years to build the generative model first before you go out and sample actual data. And no, let's think about what you're thinking, okay? That's the very first step. And in this case, we didn't estimate anything. What we did was we built a generative model to say, if it's this way, what do we get? That's a generative model. We used a counting mechanism in it, all the if statements, all of the indexes, all of the rands. Okay, all of that is counting. And we actually said, if it's all like this, then this is what we can expect, inference. And this sequence is the analytics supply chain, in a sense, the analytics life cycle, the analytics decision chain before you get to a decision. The next thing after infer is make a decision. But this is the analytics process or workflow. And I think we did it. I think we did the whole thing. I like this example because it's one and forced us to think about not just parameters, but their relationships. And did a little bit of this as well. And finally, all of this, what does the model actually look like, but coded up in the weird codes of indirect match, index match, indirect, building the histogram and all of that. Okay, I'm gonna cut this at this point, if that's okay with everybody. Are we pretty much, well, we lost Francesca. I think we're pretty much done. I'm just going to stop the recording. Charlie, thank you for leading the charge here. I'm going to stop the recording. If we want to have any further conversation, we certainly can. But again, thanks everybody for being here in spirit, at least.
I